Now, let's see. So let's start editing some of these definitions and see what happens. So now everything needs, all type interpretations need to be defined with respect to a world, which is the pair of a step index and a store type drawn from store type K, right? So when do true and false behave like they have type bool? Do they care about what the step index is? Do Booleans care about the step index? Do we care about the store typing? No, right? So it remains exactly as it is. What about functions? What do we do with functions? Remember we were doing this future world thing already? We were saying, okay, if I want to know that a function has type or behaves like it has type tau1 or tau2 for k steps, what do I do? Well, I might apply it either now or at some point in the future. And j, going to a j less than k was a way of going into the future, into a future world. And then in the future world, we wanted some value that behaved like it had type tau1 in the future world. So we're just going to continue with our world analogy and try lifting this to that. So instead of just going into a future world dictated by steps, right, we now need to say we want to go to a future world that looks like this, j psi prime, and it better be a valid future world, which I'll define in a second, of our current world, k psi. So k psi is our current world. At some point in the future, where this is the world that describes what world, the shape of your store and how many steps you have left, if we are given a value that looks like it has type tau1 for in world j psi prime, then after beta reduction, we expect to get an expression that looks like it has type tau2 in the world j psi prime. Right, so everywhere that I had j's, I just put this psi prime. And I need to define this notion of what the valid future worlds are that I can go to. All right, and this is the sort of thing, this is called the accessibility relation for those of you who are familiar with possible worlds models. It describes when you can go from a current world to a future world, what future worlds are valid for us to consider. Okay, yes?
So when you say spelled out on the board, that's actually, you're talking about the set of worlds.
This is the set of worlds, just like this is the set of worlds.
Okay, and just to be clear, so the set of worlds, its elements are worlds in the form where I guess you would enumerate all possible instances of store type.
Yeah.
Okay.
Okay. So we need to define okay, so what worlds should be valid to go to in the future? So in the future, we have possibly fewer steps left, right? And what might happen to the store typing? If you, the store could grow, right? So between now and in the future, when we have j less than k steps left, we may have done some allocation, right? We may have created some new ref cells. So the store may be larger, which means that the psi may be larger. So we need to allow for that, all right? Okay, so, but we also need to make sure that all of the locations that were in this psi, right? If this psi said that location L1 has to have type tau1, then this psi better say the same thing, because we want type preserving updates, right? We want to keep the same, we want to make sure that locations will always have those types in the future. Okay, so those are basically the things that we need. So we're going to say that j psi prime is a valid future world or of k psi, or j psi prime extends k psi, if j is less than or equal to k, and for all locations in the domain of psi, what should be the case? Right, those locations appear in psi prime, and their types should be the same, right? So this we have to write as psi prime L. Basically, what we want to say is that psi prime L is equal to psi of, to psi of L. But we need to do this sort of thing with the world as well, right? Because ultimately what we want to do is compare the sets of values in these. So we'll say, do we want to do for all j less than Okay, no. We'll just say j minus 1 psi prime approximated to j minus 1. This gets a little bit hairy, but you're just basically making sure your world is well formed and going lower a step, is equal to this thing applied to j minus 1 psi approximated to that. Right? Okay. Now, what do we have left to do? Well, so this was sort of a straightforward extension, but let's look at expressions now. When does an expression behave like it has type tau? So again, our world is now described by k. Oh, okay. Wait, we're not passing either to either. Wait. So this says, if you ignore this stuff, right?
I'm asking about this.
Oh, you are asking about that stuff. Okay. So basically, you want to take the set psi prime L and compare it to the set, or the function psi prime L, and say that it's equal to the function psi of L at the restriction, at that restricted world, or more approximate world. So we are passing, let's see, psi prime. This is also a prime, it's just gotten, so both of these are primes. Is that basically the question? And, or are you then wondering why that makes sense?
No, I see what.
Yeah, because I mean, if I started to sort of write W's here, right?
Yeah, this is always the later world that we're interested in.
Exactly.
Right.
Yeah. So we'll always use the later world to approximate that, right? We don't want to ask the question. We don't want to say that these two contain the same type in the current world. We only care about what happens when we get to the future. Okay. All right. Okay. Psi prime is the later world, right? Or psi prime is part of the later world. This one's later, this one's the current world, and this one's the future world. Sorry? The definition of type n at the very top? Oh, okay, you're right. Thank you. Forgot about that. So I said I would come back to this part of the definition of type n, right? So before, we needed our types to be downward closed. So if a value belongs to the type now, it better belong to the type in the future. Well, let's just edit our notion of future, right? So we need to say for all k, for all k psi j psi prime, such that if j psi prime extends k psi, then if a value belongs to a type interpretation in a current world, then it should belong to the type interpretation in a future world. Okay? So again, just the same downward closed sort of monotonicity property. Extension under future worlds. Okay. All right, how do we determine if expressions behave like they have type tau now? What are we doing with an expression in that definition? We're running it, right? We're evaluating it down to an irreducible. Does this operational semantics, does this even make sense anymore? No, because the form of our operational semantics is on the board behind, but it's, you need to have a store, right, in order to run a program. So we need to have an SE steps to an S prime E. and say something about that S prime, E prime that we get to being an irreducible state. But how do we pick the store that we want to run with? We need a store that satisfies psi, right? Exactly. So this requires some major space. Okay, so we need to pick a store S such that S satisfies psi, and I'll define this in a second. And we're going to start running this term when we have k steps left. So we want the store to satisfy psi for k steps. Okay? And now when we have this store, we want to say, let's go run E in this store, which should be good, right? Because E satisfies our store typing. If this reduces to a configuration S prime, E prime in j steps, where j is less than k, just like before. So we've used up j steps to evaluate to this S prime, E prime, which is irreducible. So we can't take any more steps now. Then what should be the case? We want to say the same thing we said before about how E prime should belong to V of tau, right? Okay. But what do we need to say about S prime? So we started out running the term in this world. Running the term may have allocated some stuff, so we may actually have grown our store typing psi. So what we want to say is there exists some psi prime such that in the future, our future is now when we have used up our j steps, right? So in the future, we have k minus j steps left. Psi prime better be a valid extension of the world that we started in, which is k psi. And the store that we've ended up with, which is S prime, better satisfy this new psi prime for the remaining number of steps that we have, which is S minus j. And the value that we got, well, the irreducible expression that we got, better belong to V of tau for, in the world that we've now ended up with, which is described by k minus j psi prime. Making sense? Kind of making sense? It's the same intuition as before, only now there's this complication of stores. All right? And the intuition really is the same. You want to just run the expression until you get to an irreducible state, and then you want to say that what you got is, behaves like this, like a value form of the type that you wanted, right? We're just doing the same thing. It's just that our notion of worlds is more complicated. So when we go into the future, before we were starting at k, and our future world was described by k minus j when we were done, when we got to that irreducible state. Now we have to start with a store that's good so that we can actually run. We have to say that the store that we end up with is good in some future state, which is a valid extension of our current state, and so on. Right? Okay. So let's define when a store satisfies a store typing for k steps. When do you think that is? Mapping from locations to values, mapping from locations to interpretations of types. So we better make sure that the domains are the same. So the domain of S better be equal to the domain of psi. And what? Exactly. So for all of the locations in the domain of either S or psi, it doesn't matter, we want to make sure that the values stored in the store, S of L, look like the thing that psi says they should look like, right? So this is telling us what the type should be, and this is the value. So all of the values in the store better have the type that psi says they should have. Only we're going to need to approximate a little bit, right? So the world needs to be appropriately. So we say that S satisfies psi for k steps if the contents of S satisfy the types in psi for k minus 1 steps, or for all j less than k steps. I'll go with for all j less than k. Sorry, I'll have to put it here, for all j less than k. And then we can just say j and take our psi and approximate it to j. Okay? All right. Yeah.
Could we abstract over the precise definition of world? Like if you just input W for flow?
Absolutely. That's a much better way of writing it. I'm just trying to sort of, yeah. Yeah, if I were writing this up in a paper, I would write W's here. Okay, everywhere that you have k psi, you can easily write W. You can even define some nice, notation for doing this sort of approximation, so it's not showing up everywhere. In some of the later papers, it's interesting that I use the word later. In some recent papers, people have been using the later operator. So later of I means, or rather later of a world, I should say. So later of a world, where our worlds look like this, right? We take it to mean basically that if k is greater than 0, then later of this world is going to be, how should I say this? Should be, let me just write it like this. Later of that world is k with psi approximated to k. So later means reduce something by 1 step. And you can define a later j as well that, subtracts more, if you like. So just to make things pretty. Okay. All right. Let's put some psi's over here and here. Here, obviously, we don't care for empty substitutions. Here, we need to make sure that we essentially pass around our psi in all the right places, right? So nothing really changes there. We still have this notion of substitutions behaving like, gamma, or values behaving like types in some world, only the world is richer. And then let's talk about how we lift this to open terms. So E behaves like it has type tau under environment gamma. Right? This is the semantic notion of typing. If for all k greater than 0, we pick a substitution. But now we need to pick a psi as well, right? So we need to say for all gamma and psi, such that gamma belongs to G of k psi big gamma. Then when you close off the term, you are going to get an expression that behaves like it has type tau in the world described by k psi. So there's something a little bit, so I'm picking a psi, and what am I constraining it with? Basically, I'm picking a set of inputs here, right? Gamma is giving me a set of inputs, a set of values to substitute for all of the free variables in here. We can think of them as our inputs. Some of these inputs may have type ref tau, right? Which means that some of these inputs may be actual locations. Yeah? Okay, so we need to make sure that those locations are appropriately typed, right? Which we'll do over here. And in situations where we are actually, where x maps to some ref tau, we'll go over to that definition, and obviously we need psi to contain some information about those locations. Okay, so basically what we're saying here is your inputs have to be, you're giving me a bunch of inputs. You better also give me a psi that appropriately describes those inputs. Okay, and then we close off our term and we can run it, and psi describes the shape that the store should have before we actually run the term. Okay? All right. So with that done, you then basically want to prove the fundamental property, and type safety follows just like it did before. And it's simply that if B is well typed, then E semantically behaves like it has type tau under gamma. Okay? And that's, again, just by induction on the typing derivation, just like it was before. So I'm not going to go into that. You know, in the appropriate places in the proof, when you, like when you do the proof for new, you will have to extend your store typing. When you do the proof for dereferencing, you'll have to go look in the store typing and say, okay, what does this store typing say about the contents of the store at this location, and so on. Okay? All right. Now let's just talk for a minute or two about what we would need to do to extend this to a binary setting. Like just the most naive thing that you can think of. Like I want to start thinking about, you know, being able to prove equivalence of some programs with references in them. What would change? First of all, I'd have to put pairs of values there, just like we did yesterday, right? And pairs of expressions, just like we did yesterday, right? We'd have that same notion of E1 being related to E2 and a V1 being related to V2. But now these V1s and V2s, let's just look at ref. Okay, so ref would say some L1 is related to some L2 at the type ref tau if something. And how will I know that L1 is related to L2? You have one program that's running. It picks location 100 to allocate at this point. And at roughly the same point, or well, not roughly, at the same point, the other program decides to pick location 200. Right, the order of allocation is not deterministic here. So you can pick you know, location 100 here to correspond to location 200 here. And you somehow in your model, you need to keep track of this sort of thing. So I don't know, the most naive thing I can think of is to change size so that it doesn't just map a location to a semantic type, it maps pairs of locations to a semantic type. And maybe you could, you know, simplistically say that those locations, there has to be a bijection between them. But bijection causes problems, right? Because surely you want to be able to reason about equivalence of programs that don't allocate exactly the same number of locations. So this is just to give you a hint of the start of all of the problems that start to come up when you reason about state. And it all has to do with, you know, dynamic allocation, keeping track of. So basically, you know, yesterday when we were talking about reasoning about equivalence, we had this relation that we were setting up, right? Now, when you want to talk about the equivalence of two programs that have state, you want to set up relations between their memories, certain invariants that hold forever in the future, right? And you need sort of a lot more. You need very sophisticated worlds in order to do that for a very large, you know, and interesting class of examples. Okay, so I'm going to switch to slides and actually talk about have references to some of this, and it'll come up again. So I just push that. Okay. So I probably have too many slides, but what we'll do is I'll try to go through parts of it, skip other parts, and then I'll just, you know, we'll put them up on the website and you can look at them for other references. Warming up. Okay, so on the first day when we started, I sort of told you, right? Logical relations, they come in two flavors, unary and binary, right? And I gave you some examples of things that you could prove with unary logical relations. It's up there on the board. And I kept repeating this intuition about, with a unary logical relation, the idea is that a program satisfies a property. If given an input that satisfies the property, you get outputs that satisfy the property. Right? And then when we move to binary logical relations, again, just examples of things we can prove with binary logical relations, the intuition becomes if you give me related inputs, I give you related outputs. Right? If you remember anything from these lectures, remember that. Okay? All right. And we've talked about some of these things. Andrew's been talking about non-interference. And you can use binary logical relations for proving compiler correctness. And I'll come back to this because I have a slide about some current work on this. But here the basic idea would be to set up a logical relation between a high-level language and the low-level language that you're compiling to. Okay, so history first. So someone was asking me, that could I talk about sort of history, and so here it is. So I think the earliest instance of logical relation is in '67. That was Tate's method. They were not called logical relations at the time. So so this is still referred to as Tate's method, proving strong normalization for simply typed lambda calculus. And then Girard in '72 proved strong normalization for system F. This is the so-called reducibility candidates method. This is, also an instance of logical relations. Then Plotkin in '73, and this is an unpublished thing. I think it's just a tech report, probably Edinburgh Tech Report. Lambda definability and logical relations. Plotkin was the first one to use the term logical relation. And if you want to Google it, it's sort of interesting. Google types mailing list, Plotkin logical relations, all right? There's a post back in '89 or something where Plotkin tried to explain why he was using the term, et cetera. And there's been discussion like every 10 years or so, someone again asks, why are logical relations called logical relations, and who coined the term? So it's interesting. Okay, Statman 85 is another very early reference. Here are two papers that you absolutely must know about and read, I think. Okay, so Reynolds in '83 had his famous paper, Types, Abstraction, and Parametric Polymorphism. So this is where he used logical relations and formalized this notion of parametricity. What type abstraction actually gives us. And then Mitchell in '86. So before '86, there's an '85 paper by Mitchell and Plotkin. Right? Yes. Okay. By Mitchell and Plotkin called Abstract Data Types Have Existential Types. So in '85, Mitchell and Plotkin realized that the thing that we call abstract data types are really just an instance of existential types. Andrew sort of alluded to this at some point in his first lecture. He said, we want mechanisms for, what are good mechanisms for encapsulation, or something to that effect. Then he put up modules up there, and he put up classes / objects, and he said, well, these are all just instances of existential types. And abstract data types are just instances of existential types, which, existential types, you sort of see them uniformly appear as, a core mechanism of abstraction. All right, and then Mitchell's paper formalizes, just like we have parametricity, the property of parametricity for universal types, for polymorphism, representation independence is the dual notion for existential types. It says that no matter what concrete no matter what concrete type you use to implement your interface, right? The client of and the interface of that abstraction of that ADT won't be able to tell the difference. Okay? Concept of representation independence. All right, and then there were lots of uses in the 80s and 90s, but so this is where my subjective sort of opinion perhaps comes in. Around 2000, I would say that there had been quite a few papers on logical relations. But until then, logical relations were sort of primarily done in a denotational style. Actually, that's not completely true, because Andrew Pitts was doing logical relations in an operational style, right? I've talked about denotational versus operational before. Denotational is where you define the interpretations of types using some mathematical objects, right? And operational is the kind of stuff that we've been doing. You want to know if an expression behaves like it has this type, run it. If you want to know if two expressions are equivalent, run them and see if they give you related values, that sort of notion. Okay. But the denotational semantics, comes with rather complicated math. So basically what happened is that, people who really had it in them to go and do this would do this. But for the most part, everyone sort of viewed logical relations as this beautiful, elegant proof technique, but only used it for simply typed lambda calculus and system F, essentially for mostly in terminating settings. And I'm grossly generalizing. There are lots of instances of this not happening, but overall, I think that people, used it in a sort of toy and idealized setting. Okay, and the main problem was how do we handle recursive types, which you need for lists and objects? How do we handle mutable references that can store objects, that can store functions? So higher order state is a term used to refer to this notion, where you can have a mutable reference that stores functions, first class functions. So, And that's sort of the main contribution of step index logical relations, that it allows you to model references in much the way that I've shown you today. You could just easily throw in universal types and existential types, and it wouldn't look any different than what we were doing yesterday without references. The intuitions carry through. The intuition scales, basically. That, in my opinion, is the biggest thing about this method. You don't have to go and sort of reinvent the mathematical machinery when you add a feature that doesn't operate well. Okay, and around 2000, there was a lot of work on type-preserving compilation first, and then proof-carrying code. And around 2000, and in the early 2000s, people started to talk about the fact that, well, we're programming languages people. We should mechanize our proofs. Benjamin's been a huge part of this, and you guys have been doing this, right? So one of the problems with those denotational logical relations is that they're really hard to mechanize, because you have to mechanize a lot of mathematics, a lot of it, before you can, even start doing interesting things. And the nice thing about step index logical relations is that the stuff that you're mechanizing, it may be tedious, the steps and so on, but it's much easier to sort of get to a complete definition, formalized and mechanized. Okay, so here's sort of a comparison slide that I had from another talk. So, but what I want to point out here is the references that are in black. All right, so this is my review of not all the papers written during this time period, but sort of some highlights. And I want you to focus on, when were we able to handle existential types and universal types together with recursive types and references. And this was sort of missing. So, okay, the stuff in black are denotational models. The stuff in blue are operational logical relations. And by the way, except for the Tate-Girard reference at the top, all of the stuff after that is binary logical relations. I intentionally left out lots of good unary stuff, but they're all binary. Okay, so the stuff in blue are operational logical relations, but not step indexed, and the stuff in red are step indexed logical relations. Okay, so what are the highlights here? Let me just sort of point out highlights. Okay, so a highlight for, oh, this doesn't show up at all. You're supposed to see shading at this point, but you can't see any shading. Okay, so the black stuff, I would say, is generally, like Boer-Burke et al., Benton Leprosy. This stuff is pretty complicated denotational semantics. They were able to handle recursive types and references. Here they were able to handle recursive types and references, but only references. You could have a ref of int, but you couldn't have cycles in the store, because that would have required more complicated mathematics. So this was the sort of stuff that people did. They cut down the space of the features that they had to model, or the language that they had to model, so that it wouldn't get super complicated. The work by Pitts and Stark is really, really nice. 93, 98. They decided to say, okay, fine, we don't care about storing functions in the heap, but we're just going to talk about references to integers, the most basic thing. But they made a lot of progress on reasoning about interesting examples where you have one program allocate more locations than the other, and there's this notion called local state, which I don't have time to explain, but it's when some locations are caught up inside a function closure, so therefore they're hidden from the client or the context, and this makes reasoning about equivalence tricky. Okay, let's move on. Okay, so step index logical relations started with Appel McAllister in 2001. And if you want to read the story about it, I'll tell you the story about it. Okay, so this happened in the context of the foundational proof-carrying code project, which was going on at Princeton. And the foundational part of this PCC project was that Andrew Appel said, we are going to do proof-carrying code, but with the smallest trusted computing base possible. So until then, George Nekula had an instance of proof-carrying code where he had, his low-level typed, let's just call it a low-level typed machine language, even though that's a slight mischaracterization. But if you think about, okay, or let's think about it as typed assembly language. Once you get to the assembly language level, you have a lot of instructions, a lot of rules, and you have a type system. This is what Greg Morissette and his students did. Right? They showed us how to do typed assembly languages. But we didn't have mechanized proofs of that typed assembly language. Right? And there was actually a proof-carrying code system for Java where there was a bug in one of these rules, because there are a lot of rules when you get to that low level, and they're much harder to understand than these simple baby calculi that we play with. Right? So having mechanized proofs there is really a nice thing. So in the context of FPCC, we wanted to prove type safety at the machine language level. Have a mechanized type soundness proof, trusting only a couple of hundred lines of higher order logic and some bits of the runtime and so on. Okay, but we were stuck. How do you? We didn't want to use progress preservation to prove type safety, because at the time the only you could use 12 at the time to do proofs of progress preservation, but 12 wasn't quite mature. I mean, now it's way better, but Andrew's argument at the time was, well, you would need to trust the schema checking and the cover checking and so on. That's all built into 12 in order to, essentially check proofs of progress preservation. I'll leave it at that. So the idea was, how can we just, trust the axioms of higher order logic and do this proof from the bottom up? And that's the style of type safety proof that I've shown you. That's exactly what we've done. But the problem was we didn't know how to handle recursive types. But anyway, there's a lot more history there. If you're interested, I can point you to references which actually have stories about this. But Andrew sat on a bus with Dave McAllister at CADE 2000 on the way back from a whitewater rafting trip. Sorry, this is irrelevant trivia, but it's interesting. And they happened to talk about this. And Andrew was like, at the time he was trying to formalize a whole bunch of mathematics from John Mitchell had a student, Mahesh Viswanathan, who had formalized this stuff, and he thought we would use that sort of semantics to do this type safety proof, but it was way too